Okay, now way back in Chapter 3, we talked about the fundamental theorem of algebra. And part of that theorem is that a real polynomial of degree n has at most n roots. Now that's actually just the easy part of the fundamental theorem of algebra. The other part says that any polynomial that has degree at least 1 has at least one root. So that's the hard part. We're not going to be able to prove that, but we will get the easy part, which is pretty impressive anyway. What's even more impressive is that we can prove it not just for polynomials with real coefficients, but in fact it's true for polynomials in any polynomial ring. Pretty cool. Okay, so we're going to have to do some preliminary propositions, which are interesting in their own right. First, when dividing a polynomial by the monomial x minus a, the remainder is f of a. You may have learned that in high school. It's an extremely useful trick. How do you prove this? Well, let's express f in terms of its quotient and remainder. We can divide f by x minus a, and using the results of the previous section, we know that the degree of r is less than the degree of x minus a. What does that mean? This has degree 1. This degree of r must be 0. R must be a constant. R must be a constant. Okay? Now plug a into both sides. F of a on the left, a minus a gives me 0 here. I have r, voila, r equals a. Okay? Very cool proposition. Here's some examples that you'll see how much time and effort that saves. Okay. Now, important special case, if a is a root of f of x, or a is a root of f of x, if and only if x minus a divides f. Okay? Proof, we do the same expression. So f of a equals 0 if and only if f of x is equal to x minus a times q of x. Okay? So this characterizes roots of polynomials. The polynomial can be divided by the monomial x minus a. Then a is a root of the polynomial. That's true for any polynomial ring, not just real numbers. Right. Another fact that we need, which is analogous to facts of real numbers, if you have a polynomial ring and two polynomials, then the product of the two polynomials is 0 if and only if either the first one is 0 or the second one is 0. Okay? Now, if you replace these polynomials with real numbers, you have something identical. In fact, real numbers are a special case of polynomials. Right now, this is an if and only if proof. We have to prove two directions. First, we have to show that p of x times q of x equals 0 if p of x equals 0, if one of the two is 0. Okay. Now, by the formula for multiplication, if p of x or q of x is 0, then the product is 0. So that's the easy part. Now we have to prove the other way. We have to prove that if the product is 0, then one of the two polynomials must be 0. That's the harder part. Okay. So we'll prove the contrapositive, namely that if two polynomials are both non-zero, then the product is non-zero. That's the contrapositive of asserting that if the product is 0, then either one or the other is 0. All right, so if you have two non-zero polynomials, and we're writing this so that m is the degree of p and n is the degree of q, that means that am is not 0 and bn is not 0. If we write PQ, we use our formula with the formula for the coefficients. Now consider the coefficient for Cm plus n. The idea is that Cm plus n is going to be the largest non-zero coefficient, and it turns out to be exactly Am times Bn. Because if you write out all the other terms, it turns out all the other terms are 0. This first term, for instance, is 0 because Bm plus n is bigger than n, so there is no term in B, there is no coefficient in B this big. This is 0. Similarly, all the other coefficients will be 0 except for this one. This one is non-zero. That means Cm plus n is non-zero. Okay, so now we have enough results to get to the punchline, which says that in any polynomial ring, if I have an equation x to the m minus c equals 0, there are at most m solutions. Okay. So suppose A1 is a solution to x to the m minus c equals 0. Then by proposition 36, it follows that ax minus a1 divides x to the n minus c. Okay, so that's what we just showed. Therefore, x to the n minus c equals x minus a1 times some other polynomial, where the degree of this polynomial must be equal to n minus 1. Okay, because the degree of the product, this has degree 1, so this must have degree n minus 1 in order to make the result have degree n. Now, if we continue this process, if A2 is another solution, then using our above result, we would have A2 to the n minus c. And we plug this into this expression for x to the n minus c. And if A2 is not equal to A1, then this is not 0. So this must be 0. That means that gn minus 1 of x must be x minus A2 times gn minus 2 of x. Okay. Now, if we continue this way, we can find distinct roots such that x to the n minus c, each time we're reducing the degree of g, each time we're getting another root. Finally, if we've done this n times, the degree of g0 must be 0, so there are no more roots. What does that mean? There are at most n roots to this equation. Now, at this point, we haven't actually proven the full fundamental theorem of algebra because we only showed it for polynomials of this form. But we leave it to you to show that the proof of the general result, where you have an arbitrary polynomial, is not that much different to this proof. Okay, that's it.